Introduction to AEAD ciphers. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we are diving into one of the most significant advances in VPN encryption: AEAD ciphers. If you have ever wondered why your VPN configuration recommends AES-GCM over AES-CBC, or what those cryptic cipher suite names actually mean, this presentation will clear it all up. AEAD stands for Authenticated Encryption with Associated Data. It is not just a fancy acronym, but rather it represents a fundamental shift in how we think about securing data in transit. Traditional VPN encryption has always been a two-step process. Encrypt the data, then add authentication. AEAD combines both operations into a single, elegant algorithm. Why does this matter? In the world of VPNs, performance and security are often at odds. Every CPU cycle spent on encryption is a cycle not spent on forwarding packets. AEAD ciphers give us the best of both worlds: stronger security guarantees with better performance. It's like upgrading from a two-stroke engine to a modern fuel-injected motor. Throughout this presentation, I'll show you exactly how AEAD works, why it's superior to traditional cipher suites, and most importantly, how to implement it in your VPN infrastructure. We'll look at real performance numbers, discuss hardware acceleration, and even peek into the future with post-quantum AEAD algorithms. The problem with traditional encryption. To understand why AEAD is revolutionary, we need to first understand the problems with traditional VPN encryption. And trust me, once you see this, you'll never look at AES-CBC the same way again. Traditional IPSec encryption uses what we call encrypt then MAC, or sometimes encrypt and MAC approaches. You take your plaintext, encrypt it with something like AES-CBC, then calculate a separate HMAC/SHA-256 hash for authentication. Two separate operations, two separate keys, two separate algorithms. It works, but it is like using two different locks on your door when one really good lock would be better. Here's where it gets problematic. First, there's the performance hit. Every packet needs to go through two cryptographic operations. On a busy VPN gateway handling thousands of connections, this doubles your cryptographic overhead. I've seen gateways max out their CPU just from the HMAC calculations alone. But performance is just the beginning. The real issues are cryptographic. CBC mode is vulnerable to padding oracle attacks. The separate MAC means you need to be extremely careful about the order of operations. Encrypt then MAC, MAC then encrypt, or encrypt and MAC. Get it wrong, and you've introduced vulnerabilities. Even implementations that get it right can be vulnerable to timing attacks. I worked with a financial institution that discovered their VPN gateways were vulnerable to BEAST attacks because they were using AES-CBC with TLS 1.0. The fix? Move to AEAD ciphers. The vulnerability simply does not exist with AEAD because the construction is fundamentally different. The diagram on this slide shows how traditional encryption leaves gaps between the encryption and authentication steps. These gaps are where attackers find their opportunities. AEAD closes these gaps by design. How AEAD works. Now let's dive into how AEAD actually works. Do not worry. I will keep the math to a minimum and focus on what you need to know to implement and troubleshoot AEAD in your VPN. AEAD combines encryption and authentication into a single operation. When you encrypt data with an AEAD cipher like AES-GCM, you get back two things: the ciphertext and an authentication tag. Think of the tag as a cryptographic seal. If anyone tampers with the ciphertext, the tag won't match, and decryption will fail. But here's the clever part: the associated data in AEAD, not all data in a packet needs to be encrypted. IP headers, for example, need to be readable by routers. But you still want to ensure they haven't been tampered with. AEAD lets you authenticate this data without encrypting it. It's like having a tamper-evident seal on the outside of a locked box. In IPSec, the ESP header is typically the associated data. It contains the security parameter index, or SPI, and the sequence number. These must be readable for the receiver to know how to process the packet. However, we also want to ensure they haven't been modified during transit. AEAD authenticates these fields without encrypting them. The process is beautifully simple. You provide the plaintext, the associated data, and a nonce number used once to the AEAD algorithm. Out comes the ciphertext and tag. To decrypt, you provide the ciphertext, associated data, nonce, and tag. If everything checks out, you get your plaintext. If anything has been tampered with, decryption fails entirely. This fail-closed behavior is a security feature. With traditional separate encryption and authentication, you might decrypt garbage if the MAC fails. With AEAD, you get nothing, which is exactly what you want when dealing with potentially malicious traffic. AES-GCM, the AEAD workhorse. Let's talk about AES-GCM, which has become the de facto standard for AEAD in VPNs. GCM stands for Galois/counter mode, and it's a brilliant piece of cryptographic engineering that gives us both speed and security. AES-GCM works by using AES in counter mode for encryption, essentially turning AES into a stream cipher. This is already more efficient than CBC mode because you can parallelize the encryption. But the real magic is in the authentication. GCM uses Galois field multiplication to create the authentication tag. Without getting too deep into the math, this is extremely fast on modern processors. How fast? In my benchmarks, AES-GCM is typically 3 to 4 times faster than AES-CBC plus HMACSHA256 on processors with AES-NI instructions. On a recent deployment for a cloud provider, switching from AES-CBC to AES-GCM increased VPN throughput from 2.3 gigabits per second to 8.7 gigabits per second on the same hardware. That's not a marginal improvement, that's transformative. But speed isn't everything. AES-GCM provides authenticated encryption with a single key, eliminating entire classes of attacks. There's no padding, so no padding Oracle attacks. The authentication is built in, so no issues with MAC then encrypt vs encrypt then MAC. It's secure by construction. The configuration example shows how to set up AES-GCM in various VPN solutions. Notice how much simpler it is. One algorithm instead of two. In Strong Swan, it's just AES-256 GCM16. The 16 refers to the 16-byte 128-bit authentication tag, which provides 2 to the power of 128 security against forgery. That's strong enough for any conceivable application. One critical point about AES-GCM: nonce reuse is catastrophic. If you ever encrypt 2 different messages with the same key and nonce, you've compromised both the confidentiality and authenticity of your data. Modern implementations handle this automatically, but it's crucial to understand when troubleshooting or implementing custom solutions. ChaCha20 Poly 1305, the mobile champion. While AES-GCM dominates the data center, there's another AEAD cipher that's taking the mobile world by storm: ChaCha20 Poly 1305. If you're running VPNs on mobile devices or IoT equipment, this is the cipher you need to know about. ChaCha20 Poly 1305 was designed by Daniel J. Bernstein, one of the most respected names in cryptography. It combines the ChaCha20 stream cipher with the Poly 1305 authenticator. The design philosophy was different from AES-GCM. Instead of relying on hardware acceleration, ChaCha20 Poly 1305 is fast in software on all platforms. Why does this matter? Not all devices have AES hardware acceleration. Smartphones, IoT devices, and older computers often struggle with AES GCM. I tested a VPN client on a Raspberry Pi. AES GCM maxed out at 45 megabits per second, while ChaCha 20 Poly 1305 hit 180 megabits per second. That's a 4x improvement just from choosing the right cipher. But it is not just about raw speed. ChaCha 20 Poly 1305 is more forgiving of implementation errors. It is resistant to timing attacks by design, does not have the nonce reuse catastrophe of GCM, even though nonce reuse is still bad, and is generally easier to implement securely. Google chose it for their QUIC protocol and WireGuard uses it exclusively. That is a strong vote of confidence. The performance characteristics are particularly interesting on mobile devices. ChaCha 20 Poly 1305 uses less power than AES GCM on devices without hardware AES in battery life tests. Switching from AES GCM to ChaCha 20 Poly 1305 extended VPN usage time by 15 to 20% on smartphones. For always-on VPN configurations, that's significant. The configuration example shows how to enable ChaCha 20 Poly 1305 in various VPN solutions. Note that it is often listed as ChaCha 20 Poly 1305 or ChaCha 20 Poly 1305. Some older implementations might not support it, but any modern VPN solution should. If your mobile VPN is draining batteries or struggling with performance, switching to ChaCha 20 Poly 1305 is the first thing I would try. Hardware acceleration and performance. Let's talk about hardware acceleration, because this is where AEAD ciphers really shine. Modern processors have changed the encryption performance game completely, and if you're not taking advantage of hardware acceleration, you're leaving massive performance gains on the table. Intel's AES-NI, AES New Instructions, has been around since 2010, but it is the combination with CLMUL, carry less multiplication, that significantly speeds up AES GCM. AES-NI accelerates the AES operations, while CLMUL accelerates the Galois field multiplication used for authentication. Together, they can make AES GCM faster than any software-only cipher. I recently benchmarked various ciphers on modern hardware. On an Intel Xeon with AES-NI and CLMUL, AES 256 GCM achieved 23 gigabits per second for large packets. The same hardware only managed 6 gigabits per second with AES CBC and HMACSHA 256. But here's the kicker. Disable AES-NI, and AES GCM drops to 1.8 gigabits per second. Hardware acceleration isn't just nice to have, it's essential. ARM processors have their own acceleration with the ARM v8 cryptography extensions. These are standard on modern ARM chips, from your smartphone to AWS Graviton servers. The performance improvements are similar to Intel, 10x or more compared to software implementation. Apple's M1/M2 chips take this even further with dedicated encryption blocks that barely impact CPU usage. But what if you don't have hardware acceleration? This is where cipher choice becomes critical. ChaCha 20 Poly 1305 is your best bet for software performance. On that same Xeon with AES-NI disabled, ChaCha 20 Poly 1305 achieved 3.2 gigabits per second, nearly twice as fast as software AES GCM. Always profile your specific hardware and choose accordingly. The performance table on this slide shows real-world numbers from various platforms. Notice how the performance characteristics change dramatically based on hardware support. A VPN gateway selection should always consider the hardware acceleration available. I've seen organizations waste thousands on upgraded hardware when they just needed to enable AES-NI in their BIOS. Migration strategies. From legacy to AEAD. Migrating from traditional ciphers to AEAD isn't just a configuration change. It's an opportunity to modernize your entire VPN infrastructure. Let me share strategies that have worked in real deployments, including some lessons learned the hard way. First, inventory your current cipher usage. You would be surprised how many organizations do not actually know what ciphers they are using. Run IPSec status or equivalent on all your gateways. Check your client configurations. I once found a client still using 3DES in 2023 because it has always worked. Create a spreadsheet mapping every tunnel to its current cipher suite. Next, assess compatibility. AEAD support is excellent in modern equipment, but you might have legacy devices. IKEv2 has supported AEAD since inception, but IKEv1 support varies. If you're still on IKEv1, this might be the push you need to migrate to IKEv2. Check firmware versions, as sometimes AEAD support is just a firmware upgrade away. The migration itself should be gradual. Start with a pilot. Pick a low-risk tunnel between modern endpoints. Configure both endpoints to prefer AEAD but accept legacy ciphers. Monitor performance and stability. Once confident, gradually expand to more tunnels. The configuration example shows how to set up cipher preference lists that enable smooth migration. One gotcha I have encountered: MTU issues. AEAD ciphers typically have slightly different overhead than traditional ciphers. AES-GCM adds a 16-byte tag, while AES-CBC plus HMACSHA-256 might add 32 bytes or more, depending on padding. This can cause fragmentation issues if your MTU is set too high. Always test with large packets and adjust MTU accordingly. Performance testing during migration is crucial. Don't just assume AEAD will be faster. Verify it on your specific hardware. I've seen cases where old hardware performed worse with AES-GCM because of a lack of hardware acceleration. In those cases, SHA-20 Poly 1305 or hardware upgrades were necessary. Finally, update your security policies and documentation. AEAD ciphers might enable you to simplify your IPSec policies since you no longer need separate encryption and authentication algorithms. This is also a good time to remove any obsolete cipher suites from your configurations. AEAD in different VPN protocols. AEAD adoption varies across different VPN protocols, and understanding these differences is crucial for making informed decisions about your VPN architecture. Let me walk you through how AEAD is implemented across the major VPN protocols. IPSec with IKEv2 has the most mature AEAD support. The RFC standards are clear, implementation is consistent across vendors, and you have multiple AEAD options. AES-GCM is universally supported. SHA-20 Poly 1305 is increasingly common. When configuring IPSec, AEAD ciphers are specified in the ESP proposals. Negotiation is automatic. If both sides support AEAD, they will use it. OpenVPN's AEAD journey has been interesting. Prior to version 2.4, OpenVPN used its own authenticated encryption construction. Version 2.4 introduced proper AEAD support, but there is a catch: you need to explicitly configure it. The cipher directive specifies the AEAD algorithm, and you must not use the old auth directive. I have seen many broken configurations where people tried to use both. WireGuard takes a different approach. It only uses SHA-20 Poly 1305. No cipher negotiation, no options, no complexity. This opinionated design is either perfect or problematic depending on your needs. For most use cases, it's brilliant. The performance is excellent, security is top-notch, and there's no risk of misconfiguration. But if you need FIPS compliance or have specific cipher requirements, WireGuard isn't for you. Secure sockets layer/TLS-based VPNs vary widely. Modern TLS 1.3 mandates AEAD ciphers. You literally cannot use TLS 1.3 without AEAD, but many secure sockets layer VPNs still use TLS 1.2 or older, where AEAD is optional. If your secure sockets layer VPN supports TLS 1.3, enable it immediately. The security and performance improvements are substantial. The comparison chart shows the AEAD landscape across protocols. Notice how newer protocols have better AEAD integration. This is not coincidence. AEAD has become the standard for new protocol development. Even protocols like QUIC and HTTP/3 use AEAD exclusively. If you are choosing a VPN protocol for a new deployment, strong AEAD support should be a key criterion. Security considerations and best practices. AEAD ciphers are more secure by design, but they are not magic. Proper implementation and configuration are still crucial. Let me share the security considerations that keep cryptographers up at night and how to address them in your VPN deployment. The most critical issue with AEAD is nonce management. Every encryption operation needs a unique nonce, which is a number used once. If you reuse a nonce with the same key, you have broken both confidentiality and authenticity. With AES-GCM, nonce reuse is catastrophic. It allows attackers to recover the authentication key. Modern implementations handle this automatically by using packet sequence numbers, but understanding this risk is important. Key rotation becomes even more important with AEAD since we are using a single key for both encryption and authentication. That key is doing more cryptographic work. I recommend rotating keys at least every 2 to the power of 32 packets or 24 hours, whichever comes first. The configuration example shows how to set up automatic key rotation in various VPN solutions. Tag size matters. AES-GCM typically uses a 16-byte 128-bit tag, but can be configured for shorter tags. Don't do it. I have seen configurations using 8-byte tags to save bandwidth. The bandwidth savings are negligible, but the security impact is severe. A 64-bit tag can be forged with 2 to the power of 64 attempts, feasible for a determined attacker. Implementation quality varies. Not all AEAD implementations are created equal. Look for implementations that have been formally verified or at least extensively audited. The major open-source implementations, OpenSSL, Boring SSL, Libsodium, are generally solid. Proprietary implementations, especially in embedded devices, can be problematic. Side-channel attacks remain a concern. While AEAD ciphers are designed to be more resistant to timing attacks, implementation matters. Ensure your VPN gateways run on systems with appropriate side-channel protections. Modern CPIs have features like AES-NI that provide constant time operations, but these need to be properly utilized. Finally, remember that AEAD protects data in transit, not at rest. VPN configuration files containing pre-shared keys or certificates need separate protection. I have seen perfectly secure AEAD deployments compromised because configuration files were stored in plaintext. Use proper key management practices throughout your infrastructure. The future. Post-quantum AEAD. As we wrap up, let's look into the crystal ball and see where AEAD encryption is heading. The elephant in the room is quantum computing, and it's going to fundamentally change how we think about VPN encryption. Current AEAD ciphers like AES-GCM and ChaCha20Poly1305 are actually quantum-resistant for symmetric encryption. A quantum computer might reduce AES-256 to effective AES-128 security, but that is still strong enough. The real problem is key exchange. Current Diffie-Hellman and ECDH key exchanges will be broken by quantum computers. Without secure key exchange, the best AEAD cipher is useless. Post-quantum key exchange algorithms are already being standardized by NIST. Kyber for key encapsulation and dilithium for signatures are leading candidates. The challenge is integrating these with existing VPN protocols. IKEv2 has proposals for post-quantum key exchange, but implementation is still experimental. Early adopters are already testing hybrid modes that combine classical and post-quantum algorithms. New AEAD constructions are also emerging. AEGIS and ROCCA are AEAD ciphers designed for extreme performance. We are talking 100 plus gigabits per second on modern hardware. They're not standardized yet, but for high-performance applications, they're worth watching. Some leverage CPU vector instructions in ways that current ciphers don't. The integration of AEAD with emerging protocols is accelerating. QUIC uses AEAD exclusively, and its success is influencing other protocols. Even IPSec is evolving. Proposals for simplified ESP that mandates AEAD and removes legacy options are gaining traction. The future VPN might look very different from today's complex configurations. My advice for future-proofing? Build flexibility into your infrastructure. Use protocols and implementations that support algorithm agility. Monitor standardization efforts, for example, the IETF for protocols and the NIST for algorithms. Start experimenting with post-quantum algorithms in lab environments. The quantum threat might be years away, but the migration will take time. AEAD has transformed VPN encryption from a necessary evil to a performance enabler. By combining encryption and authentication, we get better security with better performance. Whether you choose AES GCM for the data center or ChaCha 20 Poly 1305 for mobile devices, AEAD ciphers should be your default choice for VPN encryption. The future is authenticated encryption, and the future is now. Thank you for your attendance. Please consider subscribing to the channel.